Alright, let's draw ourselves some free body diagrams, folks. So, the trick here is you need to make sure that the length of the arrow represents the magnitude of the vector and the direction of the arrow shows the direction of the force vector. You always start in a free body diagram, start with either a dot or a box. I like to use a box. The force vectors always start at the box and move outwards from it. So even if something's being pushed from below, I draw the arrow above because I always want to show the arrow representing, starting at the box and then moving outwards from the box. So here we go. This box slows down as it moves to the right. So that means that if it's slowing down in the positive direction, the net force must be in the negative direction. So what I'm going to do is I'm going to draw a box. And I'm going to first remember that if I'm on a floor, there are definitely, all objects are pulled down by gravity. So I have mg. Remember, let's get in the habit of writing, instead of saying the force of gravity, let's write mg. It really will help us as we go through this unit and other units to always think of the force of gravity as mass times the acceleration of gravity, mass times 10 meters per second squared. Now, since we're on a floor and that floor is not allowing the box to sink into it, the normal force has to have the same magnitude as the force of gravity. So therefore, these two arrows should be in opposite directions and equal in length, indicating that there is no net force in the positive or negative vertical direction. However, there is a negative force acting on it in a horizontal direction because it's moving this way, but it's slowing down this way. So there must be a force acting in this direction. That force would be the force of friction. So there's my free body diagram there. Let's try our next one. Skydiver. Well, let me draw my skydiver. There she is. Okay. She's accelerating to the ground at 10 meters per second squared. That means there's no other force acting on her, otherwise her acceleration would be more or less than that. The only force acting on her must be the force of gravity, which points in a downward direction, and I'm going to label it mg. Let's try our next one. Now our skydiver deployed her parachute. Let's draw my skydiver. She still weighs mg. But now she's encountering a friction force that's twice the magnitude of her weight. So I need to draw an arrow that's twice as long as this one in the opposite direction. So wish me luck. Here I go. Whoops, that's the wrong thing. So much for my luck. Here I go, and it's going to be twice as long as the first one. I'm going to label that one the force of friction. Now, this next one, the skydiver chute is open, and she's falling to the ground at a constant velocity. My friends, we always need to look for that term, constant velocity. Constant velocity means either, that means dynamic equilibrium. That means the forces are equal. The object is not accelerating. So that means that our downward force, which is mg, the force of gravity, must be completely balanced by an equal upward force, the force of friction. Let's keep going. A box is being pushed to the right across a carpeted floor at constant velocity. So there's a force acting on it, moving it to the right, but the carpeted floor is apparently putting a friction force on it that's keeping it from accelerating. Now this object is not falling. So one thing we've got to remember, if the object is not falling, all right, we have to have a normal force acting on it that's equal to the force of gravity downwards. For this assignment, that really doesn't matter that much. But once we start putting these objects on sloped surfaces that aren't horizontal anymore, that's going to be quite important. Now, let's see. So it's being pushed to the right at a constant velocity. So it's being pushed to the right. So there must be a force applied to it in that direction. That's supposed to be an A. Sorry, it doesn't look like one. And then there must be an equal amount of frictional force acting in the opposite direction, which is keeping it in dynamic equilibrium. So I'll say a force of friction. So again, notice constant velocity. When you see that, you know the force is equal. Here we are on page 2. We're going to do the exact same thing as we've done on page 1, but now I'm giving you a picture and asking you to represent that picture as a free body diagram. So here is the person who is hanging from the trapeze thing I've got there. Now, there is a downward force of gravity acting on this person, which we will label mg. Now, because the person is hanging there, the person is in static equilibrium. What that means is that the total amount of upward force has to equal the total amount of downward force. But that total upward force is divided into two places. So I'm going to have to draw two upward arrows representing an applied force, or actually a tension force. And that tension on each rope has to be half of what this one is. So I'm going to try to draw two arrows that are collectively, if I add those two arrows together, this one and this one's length should add up to this one. That's how I try to represent this. And we're going to call each of these a force of tension, because it's a rope. Alright, number 7, a box rests on the floor. It is being lifted by a rope with a force equal to 1/3 the weight of the box. Alright, let's see how well we're understanding this. I have a box. It has a weight of mg. Now, it's got a force acting upwards by a rope, and that's making a tension force equal to 1/3 of this length here. So I'm going to try to draw an arrow that's 1/3 as long as this. And keep in mind, it's hard to draw with this stylus, but here I go. There it is. And I'm going to label that one force T for tension. Now, because this is not going anywhere, since it's in static equilibrium, that means that the normal force, the force that's keeping the box from sinking into the floor, there's a normal force that always acts perpendicular to the surface. Instead of having to be equal to mg in this case, it has to be equal to 2/3 mg, because 1/3 of that weight is being taken up by the tension. So I'm going to draw an arrow that's 2/3 as long as the weight vector, and I'm going to label that one force normal. The idea is that this arrow and this arrow, if you add them together, the total length should equal this one here. That way the forces cancel out. I have a box that is slowing down as it slides to the right. Pretty cool diagram, huh? It's like an oil drop diagram. So here we go. Now, that box is got a weight of mg, and it is not sinking into the floor, so there is a normal force that is just as large as the weight. Since it is slowing down, there has to be a force acting in the negative direction on it, and that would be a force of friction. Here I have a box is being pulled by tug of war in two directions. And let's see what we have here. The box is encountering friction. Oh, look at this. It's moving to the left at a constant velocity. So there's a couple pieces of information here that are important. The fact that it's a constant velocity means the sum of the forces equals 0. It is in dynamic equilibrium. The fact that it is moving to the left tells me which direction that the friction vector is going to point. It always points in the opposite direction. It will have to point to the right. So let's try drawing this then. Here is my box. I have a force of tension acting in this direction, which I'll label Ft. There is a force of friction acting in this direction, which I'll label force F. And now, if I drew it correctly, which is hard to do with a stylus, the combination of this force and the pulling force, the tension force caused by this one, the two together should add up to be the length of this one. So let me try and see how I do here. Hey, what do you think? So if I've drawn it correctly, this vector plus this vector have the same magnitude when added together as this one, which keeps the system in dynamic equilibrium. You know what? These book problems, they can get inside your head, but if you just do a free body diagram, they're not that hard. And I know they like to ask these ones on the AP test. So let's just try this. A book was dropped out of a window and it is slowing down. Now it is slowing down in this direction. So that means it's moving in a negative direction. Slowing down in a negative direction means you have a positive acceleration. So let's just try doing this. Since it has a positive acceleration, slowing down in the negative direction, that means the net force must be in the positive direction. So what I'm going to do is I'm going to draw force mg. The book is being pulled down by gravity. Don't forget that. But it must be pushed up with a greater vector than that, which is causing it. So I'll call that force applied. Or if you prefer, I guess you could say that their hand represents a horizontal surface that's making a a normal force. I guess you could label it that way as well. Okay, but the point is, this arrow here must be longer than this one to indicate that the net force is upwards, causing it to slow down in the negative direction. Now again, I have a book. The book is slowing down, but it's also moving upwards. So this book is slowing down in a positive direction. If you slow down in a positive direction, you're encountering a negative acceleration, which means you're encountering a negative force. So what that means is the net force must be in a downward direction. So here's the force of gravity, mg. The upward force must be less than that because our overall force is downward, causing it to slow down in a positive direction. So I'll make this force applied. Okay, now let's bring it all together now. I've got a 45 kilogram student in an elevator accelerating upwards at 2. Draw an FBD. Alright, so here is my student. Here is the force normal acting on the student. Here is the mg, or weight of the student. Let's see, this is 450 newtons. And I want to know what the net force is acting on the student. Well, the net force is just going to be found by saying, in this case, I'm going to say F equals ma, our old friend's Newton's second law. And I know what the mass of the person is. The student is 45 kilograms. That's a kilogram if you can't tell. The acceleration is 2 meters per second squared. So therefore the net force acting on the student is 90 newtons. Now, what is the magnitude of the normal force? Well, the thing to keep in mind is that the net force, which I'll say the F net, is really equal to the sum of the forces acting on the system. So the sum of the forces acting on the force is just going to be F, in this case, the force of gravity plus the force normal. So let's substitute in. The force net is 90 newtons. That equals the force of gravity, which, by the way, acts in a negative direction. So I have to write not 450, I have to write negative 450 newtons. Really got to watch those positive or negative signs. Always think in terms of direction, plus the force normal. So this means I have to add 450 to both sides. In order to get F in by itself, I have to add 450 to both sides. So when I add 90 plus 450, what I get is 540 newtons equals the normal force. So this one up here is 540 newtons, and that's why this person is accelerating upwards. Okay, so now I have a box that is being pulled to the right. So here's my box. It is being pulled to the right with 440 newtons. And it's also being pulled to the left with 260 newtons. And it is encountering 110 newtons of friction. Now, at this point, since we haven't been given any information about the motion of the box, we'll assume it is starting from rest. And since we notice that this force is larger, that would imply that the box is going to be accelerating in this direction, or certainly moving in this direction. So therefore, the force of friction has to be in the opposite direction. So I'm going to put another arrow over here, and that's my friction force, and that's going to be 110 newtons. So then, let's also remember I've got gravity pulling down on it, and I've got the normal force, which is balancing out the gravitational force. And I haven't been given any information about these two forces, but it turns out it doesn't matter because they're going to cancel each other out. It's not going to be moving up or down. It's not going to be accelerating up or down. What is the net force acting on the box? So the net force is just going to be the sum of the forces. So the force net equals the sum of the forces, which equals, let's make it 440 plus negative 260 plus negative 110. And when I add all those up, the net force is going to equal 70 newtons. So therefore, what is the mass of the box? Well, to find the mass of the box, I'm going to use old Newton's second law, F equals ma. And the net force is 70 newtons. I'm looking for the mass of the box, and I happen to know this box is accelerating at 1.5 meters per second squared. So I have to divide 70 by 1.5, and when I do, what I'll find is that it has a mass of 46.7 kilograms. Let's try another one. A 2.5 kilogram book is moving upwards while being pushed in an upwards direction with this much force. Here's my free body diagram. I have a book. It is being pulled down. Well, it has a mass of 25, and here's why we like to write mg for the force of gravity. So I know, because it's a 2.5 kilogram book, that the downward force of gravity is 2.5 times g, which is 10. So it's a 25 Newton force of gravitation acting downwards. And I have a 12 Newton applied force acting in an upwards direction. So the net force on the book is in the negative direction, and it is negative 13 newtons is the net force acting on the book. Now, let's see what we have here. We're going to say, how long will it take the book to stop moving? So I'm looking for time, and I know about the force, well, and I know the mass. So I had to find the acceleration first. So I'm going to start by saying, okay, I'm going to use Newton's second law written this way, A equals F over m. The net force is negative 13 newtons divided by the mass, which is 2.5, and I'll get an acceleration, therefore, of negative 5.2 meters per second squared is the rate at which this book is accelerating in the negative direction. Now, it's moving upwards at this rate right here, and so I want to know how long it's going to take. So I think the kinematics equation that's most likely to help me would be this one. V final equals V initial plus A t. So V final is going to be 0. V initial is 4 in the positive direction, plus the acceleration is negative 5.2, and I want to solve that for time. So what I end up getting is time equals negative 4 divided by negative 5.2. So therefore the time is going to equal 0.77 seconds. Okay, on the last page here. So I'm going to draw a free body diagram for, I have a fireman. Here he is. And he is a 75 kilogram firefighter, so therefore he's pulled down with force mg. M is 75, g is 10, so it's 750 newtons. Remember, the force of gravity is mg. Now, let's see, he grips the pole, producing an upward force, which is a little bit larger. Let's connect that with 1,000 newtons. And I don't have any other forces acting on the system that I'm aware of, so the net force is going to be positive 250 newtons. 250 newtons in a positive direction. How fast is he going when he reaches the force? So I'm looking for velocity. And so if I'm going to do that, I have to know something about it. I cannot use kinematics equations unless I know what the uniform rate of acceleration is. So let's just use Newton's law to find that. So I'm going to say the acceleration of this here fireman is going to equal the force acting on him divided by his mass. Now, we determined the force acting on him is 250 newtons. His mass is 75 kilograms. So therefore, the acceleration of this firefighter is going to be 3.3 meters per second squared in the positive direction. So if I want to know how fast, I think I'm going to have to use the equation. Let's see, I know how fast he was going to start with. He was going 5 meters per second to start with, and now I want to know what he ends up at. So that sounds to me like this equation here. V squared equals V naught squared plus 2a delta x. Now we're going to substitute in there. I'm looking for the final velocity, so I'll leave that alone. It's going to make it easy to solve this. V naught is 5 meters per second, so I'm going to say 5 squared. I'm going to leave off my units for right now, naughty me. Plus 2 times, his acceleration is positive 3.3. And here's where I got to be careful. He's going to be displaced 2 meters downwards, which is the negative direction. So this next one has to be times negative 2 meters. So when I run all this through, what I'll find is that V squared is going to equal, let's see, if I do all that, I'm going to find V squared equals 11.8. 11.8, which is what you get when you say 25 plus negative 2 times 3.3. And then I had to take the square root of both sides. So if I take the square root of both, what I'll find is that V equals the square root of 11.8. And the square root of 11.8, let's see, what's that equal? 3.4 meters per second. That's 3.4 meters per second. So this makes sense, doesn't it? Look, he was going 5, he gripped the pole, he ended up going 3.4. Isn't it amazing how physics works? Alright, what do we got now? Now we've got a initially at rest car. Okay, good grammar. A comma initially at rest car. A car initially at rest is being pushed. Alright, so let me just draw this car here. Alright, whoops. Here's my car. Alright, let's see. I have no information about the mass of it, so I'm just going to say, well, here we have mg, whatever the heck that happens to be. And I suppose I can find that out later, but for right now, I know that the force normal is going to be equal to it because I have no information about the car accelerating in a vertical direction. So, it's pushed by person A, is being pushed at 200 newtons. Now here's the thing, it's weird because you might think, well, if you're behind the car and you're pushing it, I should draw the arrow here. But you don't do that with free body diagrams. You always start at the object and draw arrows in the direction of the force. So therefore, even though it's being pushed from behind, I'm going to draw an arrow here and label it 200 newtons. It's also being pushed this way by another person with 350 newtons. And it's actually being pulled by another person who's pulling it this way with 150 newtons. But it's encountering 300 newtons of friction. So I had to go this way with 300 newtons. So when I add up all my forces, so the net force is going to be found by taking the sum of all these forces. So the sum of these forces equals negative 300 plus 200 plus 350 plus 150. Add up all of those, and what you're going to find is you have a net force of 400 newtons in the positive direction. So now, after 8 seconds of these forces acting on the car, it has traveled a certain distance. What is the mass? Well, I don't have one equation that will do this, but here's what I know. I have a time, and I have a distance, and I know I have a force acting on it, so I should be able to figure out how fast it's accelerating, and from that I could find the mass. So let's try this one here. I'm going to use d equals 1/2 at squared. Now for d, I'm going to substitute in 21.4 equals 1/2 of a times 8 squared. I'll be right back. I hear my food is ready. So therefore, what we'll have is, let's see, I will have 2 times 21.4 divided by 8 squared is going to equal A. So therefore, A equals 0.67 meters per second squared. Now if I want to know the mass, I'm going to use Newton's second law. F equals ma. The net force is 400 newtons. The mass I'm looking for, the acceleration is 0.67. And when I solve for the mass, what I'll find is that the mass equals 597 kilograms, which is a very reasonable amount for a car to have, I suppose. Alright, are we ready for our last one? Parting is such sweet sorrow. A bungee cord is pulling a box, so let me just draw my box. A bungee cord is pulling it to the right with 40 newtons of force, while another bungee cord pulls it to the left with 55 newtons of force. Now, of course, the box, being in a gravitational field, has weight mg, and therefore it has a corresponding normal force Fn, and those two are going to cancel each other out. So, let's see, the box experiences an unknown amount of friction force, but the box is moving to the left and slowing down. Since it's moving to the left, I know the friction force must be exerted in this direction here, and I don't know what that friction force is. Okay. Alright. What is the net force acting on the car? Well, I happen to know that the car, I'm going to use Newton's, I can't just add up the forces like I would in many of these, because I can't just take the sum of them, because there's one of them I don't know. So I'm going to find the net force using Newton's second law. Newton's second law says that the net force acting on a system is equal to the mass of the system times the acceleration of the system. And therefore, the mass is 35 kilograms times the acceleration. Now, it is moving to the left, but it's slowing down. So if it's slowing down when it's going in this direction, that means the acceleration must be going this way. So it has a positive acceleration. It's slowing down in the negative direction. So therefore, I know that this has to be a positive acceleration, even though it's moving in the other direction. So I'm going to put positive 1.4 meters per second. And when I multiply that through, I get 49 newtons. Alright, so my net force is 49 in the positive direction. So what is the magnitude of the friction force? So I know that the net force equals the sum of the forces. So I'll call it force 1 plus force 2, those are both bungee cords, plus force friction. So let's try this here. The force net is 49 newtons. And I have, let's see, a force of negative 55 plus positive 40 plus the force of friction. So when I solve that for the force of friction, what I'm going to get is the force of friction equals 64 newtons in the positive direction.